It is early July 1944, deep in the agricultural labyrinth of the Normandy bocage. The rain has been falling for days. A 30-ton machine swallowed by heavy mud is trapped by the sheer suction of the earth. In a narrow lane surrounded by impenetrable earthen banks, he shines his light on the severed track. He checks the drive sprocket. He determines the hull is intact and the transmission still functions. The verdict is passed. The tank is theoretically recoverable. It can fight again. That decision did not change the brutal physics of the Normandy environment. The vehicle was still a 60,000-pound block of cold steel, mired in thick clay, wedged tightly between impenetrable earthen banks. A technical classification from a mechanic did not break the powerful suction of the mud. The inspector had decreed the tank salvageable, but he could not physically pull it out of the ditch. The standard wheeled wreckers were still entirely useless in the flooded lanes. The heavy gantries still could not be deployed. If the Allies were going to make good on their doctrine of forward repair, they needed a machine capable of exerting massive leverage in a confined space. They needed a vehicle that could survive indirect fire while dragging 30 tons of dead weight directly out of the earth. Through the driving rain, a massive shape rumbles down the flooded Norman lane. It possesses the exact lower hull, tracks, and engine block of a standard Sherman tank. But instead of a rotating armored turret mounting a 75mm gun, it features a fixed, boxy superstructure. A towering steel A-frame boom rests folded back over its hull. This was the M32 tank recovery vehicle. It was the Allies' direct answer to the physical trap of the battlefield. No heavy lifting equipment can safely reach it. You cannot tow a sunken tank out of a flooded ditch with a standard half-track. The fundamental genius of the M32 was its footprint. The Allies understood that the only machine capable of reaching a tracked vehicle in impassable terrain was another tracked vehicle. Because the M32 was built on the exact same chassis as the tanks it was designed to rescue, it carried the same ground pressure. Where the rubber tires of heavy 10-ton trucks sank helplessly into the clay, the wide steel tracks of the M32 floated over the mud. It could traverse the same ruined fields, navigate the same narrow hedgerow gaps, and survive the same indirect artillery fire as the frontline armor. But reaching a sunken tank was only half the equation. The M32 still had to break the immense suction of the earth. Inside its armored hull sat a massive, gear-driven Garwood winch capable of a direct 60,000-pound pull. Yet raw power was useless if the recovery vehicle could not grip the ground. If an M32 simply attached a cable to a bogged-down Sherman and engaged the winch, the recovery vehicle would drag itself forward through the mud long before the sunken casualty broke free. The solution was found in geometry and anchoring. When an M32 positioned itself in a narrow lane, the crew dropped heavy, spade-like steel brackets attached to the rear of their hull. As the winch tightened, the recovery tank was pulled backward. You cannot bring a massive gantry crane into a fire-swept agricultural zone. The Germans know this because when their own heavy Panthers and Tigers, driving these sharp spades deep into the unyielding earth, the harder the winch pulled, the deeper the spades dug. The M32 used the very landscape that had trapped the Sherman to hold itself firmly in place. Then came the mechanics of force multiplication. The recovery crew would wade waist-deep into the flooded ditch, hauling heavy snatch blocks. These were massive, industrial-grade steel pulleys. Instead of running a single straight line from the M32 to the dead tank, the mechanics ran the steel cable through a block attached to the casualty's towing lugs, and then secured the cable back to the front of the M32. By using a single pulley system, the crew instantly doubled their mechanical advantage. A 60,000-pound pull became 120,000 pounds of unrelenting tension. The operator engaged the power takeoff from the tank's main engine. The thick steel cables rose out of the mud, vibrating under the extreme torque. The water around the sunken Sherman began to bubble and churn. With a loud, wet tearing sound, the vacuum of the heavy clay was broken. The 30-ton machine scraped violently out of the ditch, sliding up the embankment and back onto the roadway. The immediate tactical problem was solved. The disabled tank was out of the trap, and the M32 could now tow it backward. Break a track in this mud. Their crews often have no choice but to set explosive charges and abandon the vehicles. Out of the direct line of fire, dropping it in a secured orchard just behind the front line. But that was only an extraction. A tank dragged out of the mud with a shattered suspension and a snapped track is still utterly useless to an armored division. The M32 had the raw strength to pull the steel from the earth, but it was not a factory. The question now shifted from pure horsepower to precision labor. Having ripped the broken machine from the earth, how did mechanics actually replace thousands of pounds of heavy steel components in a muddy field without a static heavy crane? The damaged Sherman now rested in a muddy orchard, safe from direct anti-tank fire, but still entirely paralyzed. Its right track lay severed in the wet grass. Two of its heavy road wheels were shattered, and the steel suspension housing connecting them was twisted beyond repair. In a peacetime depot, replacing these massive components required a clean shop floor, hydraulic jacks, and overhead chain hoists. In the Norman reign, it required a profound feat of industrial foresight. The secret to the Allied repair system was not just in the heavy recovery vehicles. It was welded into the very design of the tank itself. When American engineers drafted the M4 Sherman, by all established rules of combat engineering, the American tank blocking the road is lost forever. They did not build it to be the most heavily armored vehicle in the world, nor did they give it the highest velocity gun. They built it to be infinitely modular. To understand this advantage, you must look at how the opposing armies mounted their road wheels. A German Panther utilized a complex, interleaved suspension system. Its large wheels overlapped each other in an alternating pattern to distribute weight evenly. If an inner wheel was damaged by a mine or a high-explosive shell, German mechanics had to physically unbolt and remove up to 5 heavy outer wheels just to reach the broken one. It was an engineering masterpiece that demanded a clean environment, heavy static cranes, and extensive downtime luxuries that did not exist in the bocage. The Sherman was entirely different. Its tracks rolled over external suspension units, known as bogies. These were heavy, self-contained mechanical blocks containing springs, road wheels, and return rollers, all bolted directly to the outside of the lower hull. The combat mechanics in the orchard did not have to open the crew compartment, remove interior flooring, or disassemble a web of overlapping wheels to reach the damage. Using the A-frame boom on the M32 recovery vehicle, the crew hoisted the side of the crippled Sherman just high enough to clear the earth. The mechanics waded in with heavy wrenches and pry bars. They simply unbolted the shattered bogie assembly from the exterior armor. But 2 mornings later, the rain clears, and the German defenders look out over the exact same stretch of road. The impossible has happened. With a heavy splash, the entire twisted unit dropped away into the mud. The necessary replacement parts arrived through 2 distinct channels. Some were rushed up from the beaches on heavy supply trucks, part of the massive logistical chain stretching back to England. But the fastest components came directly from the cannibalized wrecks left on the front line. A forward salvage team had already stripped a pristine suspension block from a burned-out hull 2 miles down the road. Using the M32's boom, the mechanics swung the salvaged bogie into place, aligned the heavy bolts, and locked the unit down. Reconnecting the broken track was an exercise in raw leverage and dangerous tension. A Sherman track was a continuous band of heavy steel blocks weighing thousands of pounds. The mechanics used specialized clamps and heavy hand winches, called come-alongs, to draw the two severed ends of the heavy track together over the drive sprocket. Under extreme physical strain, they hammered a single steel wedge pin through the track links, sealing the loop. What would have been a catastrophic, factory-level repair for a defending panzer crew was resolved by American mechanics using salvaged parts, a mobile boom, and accessible bolts. The vehicle was mechanically whole once more, but explaining the modular engineering of the tank only covers the blueprints. It does not capture the human friction. The wartime manuals assumed daylight, rested men, and clear visibility. The reality of the Normandy campaign required the 30-ton carcass is gone. There is no wreckage pushed to the side. There are only deep, fresh gouges in the mud. This heavy industrial labor to be performed under the most extreme physical constraints imaginable. To understand how the system truly functioned, we must look at what it actually felt like for the men forced to rebuild 30 tons of steel in the dark. It is 2 in the morning. The rain is still falling steadily through the leaves of the orchard. To rebuild a 30-ton machine in a combat zone is not a clean, clinical process. It is an exercise in misery, brute force, and profound physical exhaustion. The mechanics of the forward ordnance maintenance companies could not simply turn on floodlights. The German lines were only a few miles away, and enemy artillery spotters were always watching. Any naked illumination would instantly draw mortar fire. To see what they were doing, the crews draped heavy, grease-stained blackout tarps directly over the cold steel of the tank, creating a dark, suffocating tent. Underneath the heavy canvas, the air was dense and poisonous. It smelled of raw diesel fuel, damp wool, sweat, and the sharp metallic ozone of welding arcs. A mechanic lies on his back in the freezing mud, wearing thick leather gloves soaked completely through with rainwater. He ignites an oxyacetylene torch. The blue flame hisses loudly in the enclosed space, heating the edge of a salvaged armor plate until it glows a blinding, molten orange, where the tank was violently ripped from the earth. Hours later, a new American armored column. Sizzling sparks drop continuously into the muddy water, flooding his coveralls. He is welding a thick patch over the shattered right hull, working by the harsh glare of the arc, while trying not to set his own saturated uniform on fire. Around him, the rest of the crew is engaged in heavy industrial labor in near total darkness. They are wrestling with 3-foot breaker bars, their knuckles bruised and bleeding from slipping wrenches. The cold rain saps their grip strength. Every tool, every bolt, and every steel cable is coated in a thick, abrasive paste of clay and gear oil. The sheer physical weight of the parts is punishing. A single Sherman track link weighs over 30 pounds, and the men must haul, align, and hammer dozens of them into place using sheer muscle and leverage. The men are operating on adrenaline, cold rations, and perhaps 2 hours of sleep snatched in the damp cabs of their trucks. They communicate in muttered curses and muffled grunts, hyper-aware that the rhythmic clanging of heavy hammers against steel travels for miles in the damp night air. There is no glory in this specific labor. No medals are awarded for tightening bolts in a flooded trench, advances through the newly cleared lane. Among the attackers is a Sherman rolling smoothly on a tight new track. There is only the crushing density of the metal and the relentless pressure of the ticking clock. The infantry expects armor support at first light. By 0500 hours, the eastern sky begins to turn a bruised purple, and the rain finally slackens. The blackout tarps are pulled away, heavy with standing water. The mechanics pack their torches, stow their heavy tools, and drive their M32 recovery vehicle deeper into the tree line to camouflage it before the sun rises. left behind in the muddy ruts, is the Sherman. It is an ugly, violently scarred machine. Its replacement, suspension bogie, is mismatched, and the fresh weld on its hull is a blackened, jagged seam. But the engine turns over with a deep, vibrating roar. The drive sprocket engages. The fresh tracks bite into the earth. The tank reverses out of the orchard and begins moving back up the narrow lane toward the front line. The exhausted men who performed this nocturnal labor were not thinking about the broader scope of the war. They were only trying to fix one machine before morning. But as dozens of these brutal, individual repairs took place simultaneously, bearing fresh, unpainted steel welded hastily over a shattered right suspension, the mathematics of the battlefield have suddenly broken down. Across the Normandy theater, night after night, they forged a mathematical shockwave. To understand how the battle was truly decided, we must look at how this grease, mud, and exhaustion compounded into a strategic nightmare for the German defenders waiting in the hedgerows. The sun breaks through the heavy overcast, illuminating the scarred landscape of the bocage. A German anti-tank commander, studying the same narrow flooded lane, where he scored a definitive mobility kill just 48 hours earlier, expects to see a rusted hulk. Instead, he hears the unmistakable low-frequency rumble of a right radial engine. Through his Zeiss binoculars, he watches a Sherman tank advance. It bears the ugly, unpainted weld scars of a recent repair, but its gun is level and its tracks are turning. This was the terrifying reality of the Allied maintenance doctrine. What happened under the blackout tarps in the dripping orchards was not an isolated mechanical miracle. It was an industrialized process happening simultaneously across the entire front. To understand the scale of this advantage, you have to look at the daily strength reports, the cold mathematics of the campaign. A German panzer division might deploy into the hedgerows with 80 heavy tanks. Over a week of brutal combat, they might lose 15 to snapped tracks, blown transmissions, and well-hidden anti-tank guns. Because they lacked the forward-tracked recovery vehicles and the modular repair system, those 15 tanks were permanently erased, turning the narrow dirt lanes between the ancient hedgerows into deep, flooded trenches of grey clay. A German anti-tank crew, this was not an isolated event. Across the Normandy front, German panzer commanders and anti-tank units were documenting the same terrifying arithmetic. From their ledger, their operational strength dropped to 65, their ability to hold the line visibly weakened. An American armored division fighting in the same sector might suffer much heavier casualties. They might lose 30 tanks to mud, mines, and German 88mm shells. By the traditional rules of warfare, an attacking force taking that level of attrition should culminate. Their momentum should break. But because the ordnance maintenance companies were pulling the dead steel out of the ditches, cannibalizing the ruins, and bolting on new suspension bogies in the dark, the Americans did not lose 30 tanks permanently. By dawn, 20 of those shattered machines were returned to the fighting line. The division's operational strength barely dipped. This was the compound interest of steel. The Allies were not just relying on the massive factories in Detroit or the transport ships crossing the Atlantic. They were recycling their own casualties in real time. The defending forces were effectively fighting the exact same tanks twice, 3 times, sometimes 4 times, in a single month. The German gunners found themselves caught in a psychological and tactical nightmare. They were executing their ambushes perfectly. They were aiming for the drive sprockets, snapping the tracks, and burying the enemy in the impassable clay. They watched the crews bail out and retreat. Yet the victories were temporary. The damage they inflicted was no longer a permanent subtraction from the enemy's strength. The climax of the armored battle for Normandy did not occur. They were winning the localized tactical engagements. They were snapping tracks, shattering drive sprockets, and leaving in a single, massive tank-on-tank engagement. It happened quietly, in the ledgers of the opposing commanders. The German army lost its most meaningful option, the ability to bleed the enemy to a halt. Their superior armor thickness and high-velocity guns were performing exactly as designed, punching holes in Allied steel. But they were only destroying vehicles. They were completely failing to destroy the system that sustained them. The Wehrmacht was trapped in a war of subtraction, fighting an enemy operating on a system of continuous restoration. The defenders could hold a crossroads, inflict devastating losses, and retreat, believing they had crippled the American spearhead. Yet the next morning, the spearhead would resume the attack with nearly the same weight of armor. This relentless mechanical regeneration fundamentally changes how we must view the battlefield. The men in the hedgerows thought they were fighting a tank. They were actually fighting a mobile factory. But this revelation brings us to the final verdict of the campaign. If the true nature of Allied armored superiority was not found in the thickness of a steel plate, what was the ultimate reality of this invisible machinery for the men who fought within it? When the German gunner in the opening days of July watched that first American Sherman snap a track and slide into a flooded Norman ditch, his logic was flawless. By the established rules of combat engineering, the massive weight of the steel, American steel bogged down in impassable terrain. They were counting their mobility kills, trusting that the brutal environment and the immense vacuum of the clay made the machine dead. He assumed he had won the engagement because he believed he was fighting a tank. He failed to understand that the vehicle sinking into the mud was merely the visible extremity of an invisible, industrialized supply chain. The question of armored superiority in the hedgerows was never really about the thickness of frontal plates, the caliber of the main guns, or the immediate physical damage a high-velocity shell could inflict. It was about recovery architecture. The German military built tactical masterpieces. Their Panthers and Tigers were engineered to dominate the 10 seconds of extreme violence when two tanks met on the battlefield. But their doctrine failed to account for the hundreds of hours of friction that followed. They required flat ground, static gantry cranes, and safe rear areas to replace their intricate overlapping wheels and heavy transmissions. The Allies designed a system built for the friction. They designed a modular tank capable of being stripped from the outside, paired it with the wide tracks and heavy winch of the M32 recovery vehicle, and pushed their triage doctrine directly into the fire-swept orchards. The opposing forces could look across the torn landscape and see the terrifying consequences, the unending waves of American armor advancing day after day, despite taking catastrophic losses. But they could not see the machinery producing that result was permanently grinding down the Allied armored spearheads. Yet the number of tanks coming at them the next morning never seemed to drop. They could not see the forward ordnance inspectors grading shattered hulls in the rain, the snatch blocks and steel cables doubling the pulling power of the recovery crews, or the brutal cannibalization of the permanently dead to resurrect the wounded. The German gunners believed they were bleeding the enemy dry, completely unaware that their opponent was continuously recycling the very steel they were trying to destroy. But a logistical system is never magic. It is not an abstract concept existing only in a quartermaster's manual or a general's ledger. It is a chain of human decisions, heavy tools, and profound physical suffering. The true weight of this operational advantage was borne entirely by the men who operated in the shadows, just behind the front line. It was the driver of the M32 tank recovery vehicle, feathering his clutch and burying his anchor spades into the earth, as his heavy winch screamed under 60,000 pounds of tension. It was the technical inspector crawling into blackened, smelling crew compartments to salvage a pristine radio or optical sight from a ruined hull. It was the welders fighting the dampness under dripping blackout tarps, the combat mechanics lifting 30-pound track links with numb hands in the freezing mud, and the unnamed laborers who hoisted shattered suspension bogies using only pry bars, sheer muscle and exhaustion. They fought their war not with armor-piercing shells, but with heavy wrenches, cutting torches, and thick grease. The defending forces believed they were fighting an army with a bottomless supply of pristine replacement tanks brought in from vast depots on the beaches. The defining image of the armored campaign in Normandy is not a pristine, factory-fresh Sherman rolling triumphantly off a landing craft. It is an ugly, violently scarred machine, bearing a mismatched road wheel, unpainted armor patches, and a jagged weld across its hull, pulling itself out of the wet earth to fight one more morning. And beside that same narrow lane, slowly sinking forever into the impassable clay, sits the immaculate, abandoned hull of a heavy German Panzer, a magnificent weapon that broke and had no one to pull it from the mud to replace the fallen. They assumed the Allies were simply abandoning their broken machines and driving fresh ones, but the truth was far more mechanical and operating far closer to the front line. To understand why that sunken Sherman disappeared from the mud, we first need to look at the exact physical trap that the Norman landscape was supposed to be. The Norman hedgerow country, or bocage, was not just difficult terrain, it was a centuries-old fortress of earth and root. To understand why standard armored recovery should have failed here, you have to look at the geometry of the battlefield and the chemistry of the soil. Dug in with a 75mm gun watches a choke point. An American M4 Sherman advances cautiously through the driving rain. The dirt was a dense, clay-rich earth that, when saturated by the endless July rains, transformed into a deep, adhesive paste. The roads were not elevated highways. They were sunken lanes worn down by hundreds of years of farm carts, flanked on both sides by massive earthen embankments topped with impenetrable vegetation. In peacetime, the established doctrine for recovering a disabled tank relied heavily on space and solid footing. The pre-war manuals assumed a firm surface. If a tank threw a track or suffered a mechanical failure, a heavy-wheeled wrecker like the massive 10-ton Ward LaFrance truck would drive up, align itself, and use its heavy booms to pull the casualty free. The mechanics needed lateral room to swing cranes, lay out thick steel cables, block the tires, and maneuver flatbed trailers. Most importantly, they needed hard ground. Without a solid anchor, the recovery vehicle would simply drag itself toward the broken tank when the winch engaged. The bocage immediately destroyed the manual. When an American Sherman slid off a narrow lane and buried its hull in a flooded ditch, it did not just weigh 30 tons. The thick, wet clay created a massive vacuum against the flat steel belly of the tank. Military engineers call this mire resistance. Physics dictated that pulling a submerged hull from deep mud could double or even triple the amount of force required to move it. The German gunner fires. The armor-piercing shell does not strike the crew compartment. Instead, it smashes into the Sherman's right side suspension. A 30-ton machine now demanded 60 or 70 tons of pulling power just to break the suction of the earth. Wheeled wreckers were entirely useless here. Their heavy rubber tires spun helplessly in the slick clay, unable to find traction. There was no room to swing a crane boom, because the ancient oaks and high earthen walls boxed them in. Recovery crews could not position themselves alongside the casualty, because the hedgerows blocked the flanks. They had to pull from straight ahead or straight behind, often on a severe incline, working within a muddy corridor no wider than a single vehicle. If a standard heavy truck tried to winch a sunken Sherman out of this environment, the immense torque would simply snap the steel cables. Or worse, the truck would slide backward into the very same ditch. The environment was a perfect mechanical trap. The German observers understood these physical limitations perfectly. They knew exactly what European mud did to heavy steel. They watched their own magnificent heavy machines drown in it daily. When they saw an American tank swallowed by the earth, their logic was sound. The machine could not be towed. Therefore, the machine was dead. But that explanation only creates a larger problem. The Germans were projecting their own logistical limitations onto an enemy that fought under a completely different set of rules. The heavy steel track snaps violently, unspooling into the mud like a broken watch spring. The tank slews sideways. The Allied commanders knew that wheeled trucks and peacetime manuals would fail in the mud. They had already built an entirely different methodology for survival. To understand why the defending forces failed to anticipate this, we first need to look at how they calculated their own victories and why they firmly believed their localized success was strategically permanent. Late June 1944. Behind the German lines near Saint-Lô, a heavy maintenance crew struggles in the relentless rain. An SD KFZ 9 half-track, the massive 18-ton towing vehicle known as the FAMO, strains its engine to the limit. Its thick steel cables run down a flooded lane to a stranded Panther tank. The Panther has a shattered final drive. It weighs 45 tons, and its wide tracks are buried deep in the Norman clay. The half-track's engine howls, the tracks spin, but the heavy tank does not move. The mud holds it fast. Eventually, the mechanics cut the cables. They drop a thermite charge into the Panther's engine bay to prevent its capture, and they walk away. This was the daily reality for the defending Panzer divisions. The German doctrine in Normandy relied heavily on a simple, brutal arithmetic, its momentum carrying it into a deep ditch. Instantly, 60,000 pounds of dead weight settle into the wet earth, sinking nearly to the hull. They possessed technically superior fighting machines. The high-velocity guns of their Panthers, Tigers, and hidden anti-tank emplacements could punch through the front plate of an American Sherman long before the Sherman could return fire. The German strategy was to trade space for time, using the dense hedgerows as an operational meat grinder. If they killed 3 or 4 Allied tanks for every loss they suffered, the invasion would eventually bleed to death in the rain. They kept careful ledgers. German commanders looked through their binoculars, counted the American hulks bogged down in the ditches, and reported massive numbers of destroyed enemy vehicles to their high command. But this arithmetic was rooted in a fatal assumption about how machines were built. It was an assumption born in the factories of the Ruhr Valley. A German Panzer was a mechanical masterpiece, tightly engineered and densely packed. It was built to maximize combat performance, not battlefield maintenance. When a Panther's transmission failed, a frequent occurrence, when forcing the heavy machine through deep mud, the crew could not simply unbolt a plate and swap the gears. Fixing it required lifting the tank's entire turret and removing heavy sections of the hull roof. The American crew scrambles out and retreats down the lane. The German gunner lowers his sights. That level of heavy surgery demanded a Strabokran, a massive 16-ton gantry crane. This crane had to be transported in pieces and assembled on flat, highly stable ground, in the flooded, claustrophobic corridors of the bocage, under the constant threat of Allied fighter bombers. Deploying a static factory crane was impossible. As a result, when a German tank threw a track or broke a gear in difficult terrain, its crew was often forced to destroy their own elite weapon. The German officers naturally projected this operational paralysis onto the enemy. They assumed the Americans were suffering the same catastrophic friction. If the mechanics of the Wehrmacht could not save a bogged-down Panther, they reasoned, then a 30-ton Sherman trapped in a flooded crater was equally doomed. To the defender, a mobility kill was a permanent subtraction from the enemy's ledger. The math made sense. What the men on the ground saw, however, was only the visible end of a much longer chain. The German calculation failed because it measured only the thickness of armor and the velocity of shells. It completely ignored the architecture of maintenance. The Allies had not just brought a massive fleet of vehicles across the English Channel. They had brought an entirely different philosophy of mechanical survival, one designed specifically to cheat the mathematics of attrition. To understand how they bypassed the impossible physics of the mud, he does not waste another shell. In this terrain, he knows the engagement is over. The machine is permanently dead. We need to look at the invisible network waiting just behind the American lines and how they decided which steel lived and which was left to die. A few miles behind the American lines, hidden beneath the dripping canopy of an apple orchard, the air smelled of diesel exhaust, wet wool, and heated metal. This was not a rear echelon depot. This was a forward collection point for an ordnance maintenance battalion. The men operating here were not factory workers safely stationed in England. They were combat mechanics, pushed as close to the fighting as doctrine allowed, often operating within range of German artillery. They worked under a distinct philosophy. Distance was the enemy of repair. Every mile, a damaged tank had to be dragged backward, cost precious time, strained limited fuel supplies, and reduced operational readiness. When a Sherman was knocked out in the claustrophobic hedgerows, the system did not wait for the battle to end. Before any heavy equipment was dispatched, a technical inspector, often an ordnance sergeant carrying little more than a flashlight and a clipboard, moved directly up to the casualty. He crawled over the blackened steel under the cover of darkness or artillery smoke. His job was ruthless battlefield triage. He had to look at a shattered machine and decide instantly if it was going to live, die, or be consumed by its brothers. The German crew understands the physical laws of armored warfare. A 30-ton machine without a track cannot move, but more importantly, the inspector classified the wounded steel into rigid categories based on time and labor. If a track was broken or a suspension bogie was shattered by a high explosive shell, the tank was marked for immediate field repair. If the engine block was cracked or the main gun disabled, it was tagged for evacuation back to a heavy maintenance depot. But if the hull was fundamentally warped by an internal ammunition fire, or if the turret was blown clear off the chassis, the vehicle was declared a write-off. Yet, in the American logistical system, a dead tank was never truly useless. It became a tactical goldmine. If a Sherman was permanently immobilized, the mechanics immediately stripped it in the mud. They took the starter motors, the pristine track links, the optical sights, the radios, and the intact road wheels. They unbolted undamaged armor plates. The dead machine was rapidly cannibalized to ensure that 3 other slightly damaged tanks could return to the fighting the next morning. This brutal, calculated recycling meant that the Allied supply chain did not always have to wait for transport ships to cross the Atlantic. The most vital spare parts were already on the battlefield, waiting to be harvested. But triage was only a decision. Suppose an inspector climbed onto the engine deck of a tank like the one we saw trapped in the deep mud in the opening hours.